Hello everyone, welcome to the final section, 4.4. In the last section, we're going to talk about some properties of integration. That meaning just a couple more examples to work through with different types of functions, rather than just polynomial, exponential, and logarithmic functions that we looked at. So again, we're sticking to definite integrals, and the first thing that I want to look at is an example of a piecewise function. So let's say we want to find the area under the curve of f of x equals, and we'll define it using a piecewise function, x plus 5 for x less than or equal to 4, and 11 minus 1/2 x when x is greater than 4. On the interval 3 to 5. Now, well, actually, you know what? Take that back. Let's go 0 to 5. We can start all the way back at 0. And this is a positive linear function, just going to cross through the x-axis at 5, or sorry, the y-axis at 5. This is a positive linear function. It has a negative 1/2 slope, but it crosses up here at 11. This thing is living above the x-axis. That's all we need to know. So we're good. On that interval from 1 to 5, everything's positive, which means we're good to go. Whatever value we get, that's the area it should, that represents the area it should be. So let's start by setting up the integral. You'll notice that this integration is broken up at these values 4, and 4 is in this interval. So I can't just go in one straight shot from 0 to 5. I have to go from 0 to 4 first. And on that piece of the interval that I'm looking at, I'm using this function x plus 5. But then as soon as I hit 4, I have to switch to this other function and go from 4 to 5, the end of where I want to be on my interval, and use this function, 11 minus 1/2 x. So these piecewise functions are sort of broken up. This one happens to be broken up at the value 4. So when I integrate from 0 to 4, I have to switch to the second function and go from 4 to 5. It makes no sense to integrate this first piece from 0 to 5. That function's not defined after 4. It makes no sense to use this function from 0 to 5. This function doesn't even exist until we hit the number 4. So we can't go from 0 to 4 using this second piece. We have to use the first piece, 0 to 4, and then add the second piece from 4 to 5. So you see I had to break it up, and then I'll just add each piece together to get the total area under the curve of the piecewise function. So let's integrate. We get 1/2 x squared plus 5x, and then evaluate that from 0 to 4. Plus, let's integrate, we get 11x minus, we're going to get 1/4 x squared. All right, so there's already a half here, and then I'll have to divide by my new power 2. A half times a half is a fourth, and we evaluate that from 4 to 5. So there is our integration. And then we just evaluate these pieces separately. All right, so I'll plug in my upper bound, 1/2 4 squared plus 5 times 4. There's my upper bound 4 plugged in, and then I subtract. My lower bound plugged in is just going to give me 0. Right? Half of 0 squared plus 5 times 0. So I'm just going to be subtracting 0 in the end, so that's gone. Now I need to add the next part. Upper bound plugged in is 11 times 5 minus 1/4 times 5 squared. And then subtract the lower bound plugged in is 11 times 4 minus 1/4 times 4 squared. So I'm just going to do each one of these pieces, and then we'll bring it all together. Exponents first, that's 16. Then I divide by 2, that's 8. Plus, this is 5 times 4 is 9. So 8 plus 9 is 7. 11 times 5 is 55. This will be 25 over 4. Let's do this. Plus 55 minus 25 over 4. Then we'll go get a common denominator. Minus, this will be 44 minus, so there's 16 divided by 4 is back to 4. 44 minus 4 is, that last piece will be 48. So it's this piece here that we've got to fight with. We need a common denominator. So I'll multiply by 4 and divide by 4. There's my common denominator. So that should give me 220 minus 25. Well, and here we have 17 minus 48. So if we do 17 minus 48, we'll actually get a negative 31. And what did I say this was? 220 minus 25 is 195 over 4. So it looks like we need a common denominator. So let's get it. We'll multiply this by 4 and divide this by 4. That gives us a negative 31 times 4 will just be 124 plus 195. All that gets divided by 4. So when I do this, I'm actually doing 195 minus 124. That'll give me just 71 over 4. You can say square units since they mentioned area. Now you can see this is a lot of fighting, right? You're doing a lot of fighting with just the arithmetic. This might be a good exercise when you use your calculator. You can start plugging in little, like I do it piece by piece by piece, and just then bring those pieces together. This would be pretty cumbersome to put in your calculator all at once, and then if you make a small mistake, you got to go hunt down that mistake. But you can see that when you look at these, it's a lot of just arithmetic. Once the calculus is done, it's just a lot of fighting with the fractions mainly. So I'll try to keep these numbers nice so it doesn't get too hectic for you. So piecewise function, just make sure you're breaking it up in the correct spot. Now, if it said to integrate this or find the area from 0 to 3, you just use the first piece, right? 0 to 3. We never even get to the part where it gets broken up. And wouldn't that be nice? But then you're not really doing anything with the actual piecewise part of things. So the next function I want to look at is a different type of function. It's the absolute value function. Let's say we want to find the area under the curve of f of x is equal to the absolute value of x minus 3 on the interval. Let's go from, let's say 0 to 4. So this one is worth a sketch here. Recall that the absolute value function has this sort of V shape to it. And so I'm going from 0 to 4. That means I want to find this area. So I want to see how much area is there. Now be careful, because this function x minus, or I should say y equals x minus 3 is actually this straight line. So if I integrate this, from 0 to 4 with the absolute value function. If I just integrate it and get 1/2 x squared minus 3x, I've integrated this linear function, which is going to pick up a bunch of negative values over here, and then after it crosses, it'll pick up some positive stuff. And this positive and this negative stuff will cancel out a little bit, and then I'll be left with this extra negative area. So be careful, because I'm not integrating this linear function x minus 3, I'm integrating the absolute value function, which means I don't want this negative version, I want the positive version. And so my goal is to get this positive value from this negative that it would have given me. If I just integrate this linear function, I get some negative stuff and some positive stuff. So the way to fix that is to integrate from 0 to 3 that linear function x minus 3 and just take the positive version. And the function that gets that done is the absolute value function. So I just want to say that I'm not simply taking the absolute value and just pushing it outside. I have to change where I start and stop my integration, because that's going to give me the positive version when I take the absolute value. But this piece from 3 to 4 is already positive. So I integrate from 3 to 4 that linear function x minus 3 with respect to x, and it will give me exactly what I want. So there's no need to mess with the other piece. It's positive, it's going to stay positive. So again, just like with the piecewise function, we had to break this up, specifically at 3, where it crosses the x-axis for the linear function. I want to take the opposite sign, because again, we're talking area, and area is always positive. Now let's do the integration. It'll be 1/2 x squared minus 3x, and I'll evaluate that from 0 to 3, but notice I want the absolute value of whatever that is. And so if I don't do absolute value bars now, I will get a negative number from this weird integration, and I don't want the negative. Plus I have to do this piece, but this piece is just fine. It's just 1/2 x squared minus 3 from 3 to 4. Nothing to fight with there. So now we can plug in our upper bound. Again, careful, I still need to take the absolute value of whatever I get here. So here's the upper bound plugged in, 1/2 3 squared minus 3 times 3, minus my lower bound gets plugged in, but that's just all 0. Now I'm just going to write 0. All right, so again, notice I'm going to plug in my lower bound 0, my lower bound 0, that's just going to be 0 everywhere. So that's out. I really just need to compute that. Plus, and again, this, I just plug in my upper bound of 4 minus 3 times 4. Oh, I see a missing x. Sorry about that. I see a missing x right here. All right, so take note of that. I probably said it, but I didn't write it. I was going too fast. Now we'll plug in our lower bound of 3. 1/2 3 squared minus 3 times 3. Again, this is a good job for, taking your calculator and doing lots of this stuff, but this isn't too terrible. This is 9/2 minus 9. But again, I still haven't taken that absolute value yet, but you can see that's going to be a negative quantity. Plus 16 divided by 2 is 8, minus 12 is negative 4, minus, this is actually the same thing as what this was, 9/2 minus 9. So let's figure out what that value is. And again, that's why these don't cancel out. Like I don't have a positive version here and a negative version here. I need to figure out what this number is and figure out what this number is. And take the positive version, because this is actually a negative value. This is also a negative value. So I'm going to have, well, common denominator, let's write it out. All right, 9 minus 18, all divided by 2. Well, that's just negative 9/2. But I need the absolute value. Minus 4 minus, we already figured out that that's negative 9/2. Right, because it's the same computation as over here. So now I take the positive version of that. Negative, negative, that's also positive. So I've got positive 9 halves minus 4 plus 9 halves. Well, 9 halves plus 9 halves is 18 halves, which is 9. And then we need to subtract 4. 9 minus 4 is 5. So a little fighting with the fractions, but eventually it gets us where we need. And it's positive, and we're talking about area, so area is positive. I got that positive number because I broke it up properly in the middle and took the absolute value of the stuff that was going to be negative from integrating x minus 3, but I just forced it to give me the positive version, thanks to that tricky use of the absolute value function. So piecewise functions, they're broken up, so you got to play that game. Absolute value functions, they're a little trickier. You can't just go straight through it because the absolute value function does not integrate nicely. So you've got to break it up. And the next thing I want to talk about is the concept of finding area between two curves. So if we have two functions, let's say I'm going to label the blue one as f of x, and the black is g of x. And let's say we want to find the area between these two curves. And how much area is actually sitting in between those two curves. It's actually not that hard to do. Basically what we do is we integrate the blue from a to b, and we'll just put down a random a and a b. Let's say we want to find the area that's in this space here. Well, if I want to integrate from a to b, first I'll do the blue, but that gives me everything under the blue, including this space that I don't want. But then I can integrate g of x, and it will give me that stuff underneath g of x. If I subtract that stuff under g of x, I'll be left with everything under the blue, but not the stuff under g, which will be that red space, which when we set it up as an integral, it'll be from a to b of f of x minus g of x with respect to x. Now, take note that this g of x is actually underneath f of x, so this is the lower function. This function has lesser values than f of x is the upper function. If I do this the other way around, if I take g of x, integrate it, and then subtract everything under the blue, oh man, that's a lot of negative. It's not going to give me the right number. It's going to give me a negative number. So first thing you want to do is identify the upper function and then subtract the lower function. And you can do it all in one integration like this. You don't have to find this integral first and then subtract that integral second. You can do the integration all at once. And another quick note, from a to b, it would be the same as if, let's say a was here, and we just wanted to find this much area, right? It's not always that we have to go finding all of the area that's enclosed between those two curves, unless they tell us to specifically. Maybe we're just finding the area from here to here. It still works. I still go from this value to this value because this is still my upper function. This is still my lower function. It'll still give me just the area enclosed in this weird little space right here. So that works as well. If we're not concerned about the other stuff, then we just don't worry about it. We go from a to b, from here to here. But if we go from a to b, and b is somewhere over here, ooh, now there's a problem. We go from a to b, we'll get this, f of x minus g of x will give us this positive area, but then they switch roles. So for this piece, if I want to find this area, I have to switch, and I have to find this part, we'll call it C. We have to find that value where they switch roles, where the blue goes under the black and the black goes above the blue. And we'll have to break this up from A to C to get this positive area, and then later go from C to B of the G of X minus F of X. All right, so you can see if they switch roles, all right, these guys switched in terms of now G of X on this, from C to B, G of X is the upper, I'm subtracting the lower. All right, so we can do that as well, even if they crisscross. Right, and who knows, they may crisscross multiple times, and then we just want to find the area of each of those pieces. If I don't switch the roles of the functions, then I get the negative, and I don't want the negative if I mean area. So this is what it's like to find the area between two curves. So let me show you an example. Let's say we pick on find the area between curves of, we'll say f of x is equal to, let's just do x plus 2, and g of x is equal to x squared. All right, so let's say we have these two functions, and we want to find the area between these two curves. Well, let's go ahead and graph them. So first we'll start with, f of x equals x plus 2 is just a linear function going through 2 on my y-axis. Let me adjust my scale a little bit here. We don't need to go underneath the x-axis so much. So here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 4, 5, 6, 7, 8, 9, 10. If we graph y equals x plus 2, or f of x equals x plus 2, or positive 2 on the y-axis is where we cross, and then we have a slope of 1. So we just go up 1, over 1, up 1, over 1, up 1, over 1. Doesn't have to be a perfect graph. We're just sketching it so we can see what we're doing here. There's f of x. And for g of x, use green. We're graphing that y equals x squared is that parabola. So there it is at the origin. 0 squared is 0, 1 squared is 1, 2 squared is 4, etc., etc. Again, it doesn't have to be the most perfect graph. I just want to show you which one is the upper function and which one is the lower function. Now, if you'll notice, there's some area between these two. I'm shading it in red to emphasize what we're looking for. Right, so this little region that's bounded by these two graphs, it's kind of trapping in this little area here. That's what we want to find. So let's take a look at these 2 points. What we want is, for these 2 points here, we want to start at A, right here, where they intersect, and stop at B, right here, where they intersect. So these 2 points are what I need for my bounds, to start and to stop. I find those 2 bounds, A and B, by setting my 2 functions equal to each other. Right? See where the black and the green crisscross? That means they have the same value. Right? That means these 2 functions are going to be equal to each other. That's when they crisscross, when they have the same value. So now let's go ahead and solve for this. which is a quadratic, which means I can set it equal to 0. I can factor this quadratic. That's the fastest way of finding these values. Again, this is x squared plus x minus 2x is negative x, so we're good, minus 2 on the end. So these are the correct factors. Setting each one of these equal to 0, I must have x is equal to positive 2. Setting x plus 1 equal to 0 and subtracting 1, I must have x is negative 1. Now we've just found the numbers that we need. We need to find this area, so I need to start at negative 1 and stop at 2. So now I know I need to integrate from negative 1 to positive 2. The upper function is f of x. I know the green, which I didn't write down here, g of x. I know the green function g of x actually looks like it lives above f of x, and for the most part it does. But the area we're concerned about here, it actually lives under f of x. So the upper function is f of x, which is x plus 2. And then I want to subtract, again, we're only concerned about right here, g of x is the lower function. I want to subtract x squared. So now we've got this, and we need to integrate this. Right, we need to find an antiderivative, which in our case is going to be 1/2 x squared plus 2x minus 1/3 x cubed. And we need to evaluate that from negative 1 to 2. So again, we plug in the upper value, which will be 1/2 2 squared. Lots of 2's flying around there. Plus 2 times 2 minus 1/3 times 2. So there's my upper bound, minus 1/3 2 cubed. Let's not forget that cube. I'll change things. Now I plug in the lower bound, which it's a negative 1. So I get 1/2 times negative 1 squared plus 2 times negative 1 minus 1/3 times negative 1 cubed. There's my lower bound plugged in. So again, lots of fractions. Just get it done, right? 2 squared is 4 times 1/2. So that's 2 plus 4 minus 2 cubed is 8. So that's minus 8/3 minus, now we go to our lower bound, plug in and compute all that. We're squaring negative 1, which is positive 1, so that's 1/2. Minus 2 times negative 1 is plus 2 because of the negative times the negative. Negative 1/3 times negative 1 cubed. Negative 1 cubed is still negative 1, so this is going to change to plus 1/3. So let's see what we got all together here. 6 minus 8/3. 1/2 plus, well, I guess let's just get a whole common denominator across the board, shall we? So we're going to subtract. I'm going to multiply this 3 times 3. That looks like 36. I'll get a common denominator there. This we're going to multiply by 3. This we're going to multiply by 6. This we're going to multiply by 2. Sorry, I've run out of whiteboard space. Getting a little tight. Again, it's all just fractions here. This will be 3 plus 12 is 15 plus 2 is 17 over 6. That was 18 minus 8 over 3, so that's 10/3 minus 17 over 6. And now we're almost done. Right, we were in it for the long haul, so this is 20 minus 17 over a common denominator of 6. That's 3/6, which is 1/2. So again, not a lot of area. It's a small space, but we found out how much area is actually between those two curves. So again, we have to identify which one's the upper, which one's the lower, and then go from there. Then one more concept you mentioned. And that is the concept of what we call average value. The average value of a function f of x is 1 over b minus a times the integral of f of x from a to b. And they'll give you the interval a to b. If the interval changes, the average value might change. So kind of, graphically, what are we doing here? Well, we're taking a function f of x, and we're looking on some interval, say a to b, from here to here. Now, we're not finding the area under the curve. We're actually dividing by the length of the interval. And if you'll notice, f of a takes on a specific value. F of b takes on, it just so happens to cross right there. F of b takes on a very specific value. But what we want to know is, this function actually kind of goes lower and then comes back up and goes higher. The average value of a function is going to be somewhere between those values. All right, so we want to know, okay, if we have these two values, what is the average value of our function? Average on average, I'm just kind of like eyeballing here. It looks like it takes on about this value over average. Here's some low values, here's some really high values, but on average, they kind of even it out. Now, if you look at a function over a different interval, let's say f of x has, let me draw my coordinates system, and then let's say we have f of x looks like this. And we look over the interval from a, see how it has a positive value, to b, see how it has a positive value. But overall, this function has a lot of negative values. So if we look at the average value of this function, it's mostly not positive. It's only got positive values for a little while here. Then it takes on a lot of negative values from this spot to this spot. This is all negative stuff. It's living under the x-axis. And then it takes on just a couple more positive values over here. So on average, I'm still here, Math Lab. On average, this function takes on some negative values. So you would expect that your average value for f of x would probably be some value down here under the x-axis, probably some negative number. All right, so again, we're only concerned at the interval, on the interval a to b, so the fact that this function takes on really big positive values before and after doesn't even matter. We're just focused on this interval alone. So let's take a function and let's find the average value of that function. So let's say I want to find the average value of f of x is equal to, and let me just pick on something here. How about e to the x plus 1 on the interval 0 to 2. So for our average value, we go from A to B, but we need to do this subtraction, 1 over B minus A. Here, let me write this out first. This is our average value formula, if you will. So it's 1 over B, in this case it's 2, minus A, in this case it's 0. So it's 1 over 2 minus 0, that's a half. And then I integrate from 0 to 2. My function is e to the x plus 1, and I integrate that with respect to x. So again, if I just integrate this, I get the, what represents the area under the curve. I get the value of the integral, but then by dividing by the length of the interval, I get the average value that this function takes on. So it's 1/2 times, now I need to integrate this, but the integral of e to the x is e to the x plus, I integrate 1, I get x. I need to evaluate that from 0 to 2. So be careful, this half is just living out front, and we'll multiply that stuff later. Let's plug in our upper bound, e squared plus 2, minus, let's plug in our lower bound, e to the 0 plus 0. Now be careful, this whole thing over here isn't 0. E to the 0 is 1. So this is going to be minus 1, because e to the 0 is 1. So it's 1/2 times e squared plus 2 minus 1, coming from this guy, which is e squared plus 1 divided by 2. Is what it is, and you can plug it in your calculator to get some sort of a approximate value out of it, if you will. Let's do it. Let's do e squared plus 1 divided by 2. Like 4.19 something. So that's the average value that it takes on. But this is the exact answer. So if it's asking for an exact answer, you leave it like this with the e in it. And then last problem that we need, and it'll be the one on the screen, I'm looking at number 45. Number 45 talks about total and average daily profit. Let me see if I can slide that over for you. There we go. That way we can see it all. It's kind of cutting off the end of those sentences. So number 45 asks for total and average daily profit. Great Green Incorporated determines that its marginal revenue per day is given by R prime of t, I'm going to write this down because it's important, is equal to 75 e to the t minus 2t. And they let you know that R of 0 is 0. Well, be careful because this is R prime. They're giving you marginal revenue, which is the derivative of the revenue, right? R function, where R of t is the total accumulated revenue in dollars on day t. The company's marginal cost per day is given by C prime of t, which is equal to 75 minus 3t. And they're also nice enough to let you know that the cost of making 0 units is 0, where C of t is the total accumulated cost in dollars on day t. So we've got marginal revenue, and we've got marginal cost, and part A for the problem asks us to find the total profit from 0 to 10, which is 0 days to 10 days, because t is in days. And then it gives us this little hint here. Note that the profit function P of t is given by R of t minus C of t, which is equal to this integration from 0 to t, R prime t minus C prime t dt. So it gives us a hint to try and push us forward. But the key thing here is it's asking for total profit, not just the profit at day 10, right? At day 10, all you'd have to do is find the profit function and plug in 10. But we want to know the total accumulated profit, all the profit that's happened from 0 to 10 days, all accrued. So we need to integrate. We need to find basically the area under the curve, right? So if we want total profit, the first thing we need to do is find the profit function. Now these are derivatives. So in order to recover R of t, I need to integrate R prime of t with respect to t. Right, there's no x here. They're talking about the variable t. So let's do that. Let's integrate, which is just finding the general antiderivative of 75 e to the t minus 2t with respect to t. Notice that we get 75 e to the t, because if we find the antiderivative for e to the t, it's just e to the t. 75 just a multiple. It's there, it'll always be there. Integrate negative 2t, we'll get negative t squared, right? The power goes up, and then I divide by 2, which cancels out that coefficient of 2. But be careful, we're not doing this on an interval from a to b, so we need that plus c back in our picture. This is R of t. Well, the nice thing about this is R of 0 is 0. So what that means is if I plug in 0 into this function, I should get the result of 0. So let's go ahead and plug that in. R of 0 is equal to 0, which is this function R of t with 0 plugged into it. 75 e to the 0 minus 0 squared. So there I am. I plugged in R of 0. Don't forget your plus c. That's what we're solving for. We can find the actual constant c. Okay, so this is 0, it's out. I'm looking at 0 equals 75. E to the 0 is 1, right? This whole thing's not 0, it's 75 times 1, which is 75 plus c. And now I can actually solve for c by just simply subtracting 75 on both sides. Ah, there it is. Our constant must be negative 75. What that means for us is that here is going to be R of t. It's going to be 75 e to the t minus t squared minus 75. I know exactly what that constant c is now. So now we can do the same thing, and we can do the same thing with our marginal cost. So now when we look at c prime of t, I can find the antiderivative of that to get c of t. So I get 75 t minus 3 halves t squared. Again, I go up a power and divide by 2, plus c, because this is just a general antiderivative. And now I notice that for c of 0, this function, c of t, I can actually plug in c of 0 and solve to get my constant. So c of 0 is equal to 0, which is equal to 75t minus 3, or sorry, 75 times 0, right? I'm plugging in 0 here, minus 3 halves 0 squared, plus c. Well, that's 0 and that's 0, so c is also 0. Right, and now we've got that constant for that function. So this tells us that our our actual function c of t is given by 75t minus 3/2 t squared plus c is 0. So that's it. This is c of t. Let me squeak that in there. There's our cost function. So now we've got our cost function and our revenue function. So now we want profit, P of t. Well, profit is just the revenue minus the cost, which is 75 e to the t minus t squared minus 75. That's our revenue. And then we subtract the cost. Make sure you subtract all of it, which means this negative sign is going to have to change stuff. So we're going to get P of t is equal to, we'll leave this out front, 75 e to the t. I do have a negative t squared and then a negative 3/2 t squared. So in fact, I've got negative t squared and positive 3/2 t squared. That's a positive 1/2 t squared. So I'm going to be combining these two just to make it a little easier on us. And then I'll do minus 75t and then minus 75 just to keep the constant on the end. Whew, okay, so there is our profit function. What do we do with that profit function? Well, now we can answer part A. We can find the total profit from 0 to 10 by integrating the profit function. So this will give us our answer that we're looking for. In this case, we're going to take 75 e to the t plus, this will be 1/6 t cubed minus 75 halves t squared minus 75 t, and evaluate that from 0 to 10. Well, the real nice thing about that is we don't have to worry about that lower bound so much. We'll have to plug in 0 everywhere, which lots of these will be 0, but this one won't, because e to the 0 is 1 times 75. So what we're going to end up doing is 75 times 10, or sorry, 75 times e to the 10th plus 1/6 10 cubed minus 75 halves times 10 squared minus 75 times 10. There's my upper bound. Now I need to plug in my lower bound and subtract all that. 75 e to the 0 plus 1/6 0 cubed minus 75 halves 0 squared minus 75 times 0. And like I said, a lot of this stuff over here is going to be 0, is going to be 0, is going to be 0. So all of this, really what I'm looking at e to the 0 is I'm just looking at the number 75 times 1, which is subtracting 75. So even that's not too terrible there. At this point, I would say, since we're talking dollars and cents, we're going to go to our calculator anyway. So I think it'd probably just be a little bit better to jump straight to the calculator. And just to save a little bit of time and space, let's take a look at part A approximated should be 1,651,209.94. I mean, forgive me for putting it up here, but 1,600 and where I find it again, $51,209.94. So again, we'll plug it in the calculator, let the calculator do all the heavy lifting. So that will be our total profit from day 0 to day 10. And then part B asks us to find the average daily profit for the first 10 days. So as far as part A is concerned, we're good. That's our total. But what is the average profit that we get? I'm going to keep my profit function. So here's my profit function. My average for part B my average daily profit is going to be 1 over B minus A, in this case it's 10 minus 0, the integral from 0 to 10 of my profit function, P of T, with respect to T. Well, the nice thing is, and this is lucky for us, the nice thing is that we already found this, and I'll circle it in green, the integral from 0 to 10 P of T dt. It's a good thing we don't have to do that twice. I just did it and got this as a result. So all I need to do is divide that number by 10. I just need to take that number, which is this integral from 0 to 10, and divide it by 10, right? I'm multiplying by 1/10, so I'm dividing by 10. And the nice thing is all that does is just move my decimal place over. So my average daily profit is going to be $165,120.99. So there's part B. So 90% of that problem was part A, right? The second part was just bringing into the picture that average daily profit, which means just dividing by the number of days, essentially. So that's it. That's everything we need to cover up to the end of this course. The very, very last section, 4.5, again, I just adjusted due to time constraints. It's something that would be very, very necessary if it was, you were going into a Calc 2 course. But since this is just applied calc, a survey of calc, and the name of however crazy this world is already, I just figured we'll omit it. So this will be the stopping point for us. I adjusted the study guide. I think there's a few questions in the math lab homework that I still want to take out that may have 4.5 stuff in it. So I'm going to go double check that right now while I upload this video. I just want to say thank you guys for, first of all, just taking the course, but sticking with the course, even through the whole, ordeal that we're going through with this coronavirus stuff. So I appreciate it. I appreciate you. Thank you very much. And please let me know if you have any questions before the final exam. Well, I guess we got to take exam 4 first, right? We'll knock that out. And then let me know if you have any questions before the final exam. I will post some more information on Canvas about the final. It's not going to be too terrible. It'll be basically just like another version of an exam we've already taken. So that's the best way to study. It's just looking at old study guides and looking at old exams. Please let me know if you have questions. Otherwise, good luck. And don't be a stranger. When I do get back to my office on campus, feel free to stop by and say hello. So again, email me. Let me know if you have questions. Otherwise, the rest of the information I'll just post on Canvas for the final exam, and you guys will be good. So thank you very much.